Welcome to podcast episode number 22 of the ISPC Tailboard Talks. I'm your host, Mark, and along with me is my co-host, Jerry. How you doing today, buddy?
I'm good, man. Thanks for including me on this one because I'm excited about it.
Yeah, I'm excited too. Grounding and bonding. What does the expert say? And so today,
The expert.
arguably, we have the expert in grounding and bonding, and so we'll get to that in a minute. Always a pleasure to sit down and talk with our guest today. I learned something every single time I talk to him, so yep, looking forward to this one.
And we have a new sponsor this show. I'm excited about that. Have they sponsored before?
One other time.
One other time. All right. So not a brand new sponsor, but a new this year sponsor. Today's show brought to you by Gritty Tools, eliminating workplace injuries one tool at a time. Gritty Tools produces USA-made high-quality tools. The GT750 and GT1500 wire pullers are battery drill operated, and no electric is required except for the drill. I mean, that's battery operated, so not powered. You don't have to plug it in. They're portable, lightweight, and easy to get to any job site. If you want to know more, visit them at grittytools.com, Gritty tools.com, or give them a call, 866-4GRITTY, 866-447-4889. I've seen these in use demonstrated, and they are pretty badass, man.
Step up from a bare wheel on the back of a Dodge pickup truck.
Ain't it, though?
Yeah, for sure.
And if that voice sounds a tad familiar, that means that you've taken some grounding and bonding classes before or listened to this young man. That was our guest today, Jim Vaughn, the expert in grounding and bonding. Now, Mark, I'm going to tell you this. I'm not a lineman, but I've hung out with them for 10 years or so. I have never known these guys not to like lunch, right? Yep. If you say, hey, guys, free food, they're gone, right? They're at it.
Yep.
We were at a conference one time, and Jim was doing his grounding and bonding class. It was a 1 hour or an hour and a half class, and the fire alarm in the hotel kept going off. And they were like, oh, no, it's a false alarm. It's a false alarm. Well, finally it went off, and it was not a false alarm, and they evacuated everybody. And Jim, maybe you had gotten 10 minutes into your spiel or so, and they put us all outside. Well, he had the last session before lunch. We're outside for 45 minutes, maybe almost close to an hour. Jim goes in to get his laptop to go to lunch, and everybody follows him back in and misses lunch to a man. And Jim ends up giving his presentation throughout the lunch break to all these guys that voluntarily skipped lunch just to hear what this man had to say. So if that doesn't tell you that he knows what he's talking about, I don't know what does.
I'm going to have to say that I am the unintentional expert. I'm going to explain why. And of course, I'm a lineman. I've been a lineman since the 70s. I'm 70 years old. I've been doing this for a very long time. And it was about 20 years ago that I was introduced to the idea of equipotential grounding. And I happened to have somebody explain it to me well. And it really aggravated me because I had been grounding for 10 years because that's what my employer told us we had to do. But we didn't know that what we were doing was not going to work in worst case events. And now I wanted to know why. Why is this the way that it is? And so I set out to find out, and the more research I did, the more upset I got. And I even asked an engineer professor of mine where I was auditing some courses at Georgia Tech, and I said, how come nobody's telling linemen about this? And he said, well, they wouldn't understand it. That's just not right. It's unfair to the industry. It's unfair to those linemen that are out there, and not letting them know what the risks are and the hazards are and how to ensure your protection was just, to me, was untenable. And so I started to especially after we got associated with incident prevention. I started to write about it, and I just have a knack for writing in a way that makes sense. And it just opened up the doors for people asking questions. I had became associated with more and more top industry experts, and we put together some extremely good presentations that connected with the industry, and so we became the pseudo experts on grounding. And ISPC, that's one of our larger courses, a number of courses that we do and teach and reteach, and it's been a good opportunity for us to help the industry catch up.
Yeah, and it's even now today is when I go around, Jim, and do grounding and bonding, it's still, I shouldn't say amazing, but you still find the folks that don't understand the why and are just still under the the thought process that I'm working between grounds, or I got and those things. And so we'll get into that here very shortly. But yeah, it's a shame we're at the place we're at right now, right? That more people don't understand the correct way and why we need to do it that way.
Yeah, and I'm inspired to address this subject again in incident prevention. Most of our readers and everybody that's associated with IP knows that I write the 101 Train the Trainer for Incident Prevention magazine and have for about 15 years. And comes out 5 times a year. And there's been a dozen times that we've written about grounding, trying to get people to understand it, and we touch on it many times in the Q&As, also with specific questions that come through. But I was inspired again because in this last week, I had another inquiry. One of the things that ISPC does is we do expert witness and consulting on litigations, which is both OSHA actions against employers and civil litigations against employers. And another one has come up with another lineman who was killed by induction current on a grounding system. So just to give you an idea, and this has really helped us to perfect our understanding and our delivery about grounding training. I have had now in the past 20 years some 40 fatal consults for fatal incidents, linemen being killed on the job. And right now we're currently handling 16 cases that are fatal cases of linemen being killed on the job. And the thing that probably bothers me the most is that there's been about 20 of those cases where linemen that were killed by the grounding that they installed for their own protection. So you get that? Linemen killed by the grounding that they had installed for protection because they thought they knew what they were doing because nobody explained to them the intricacies that are involved in current flowing in a grounded system. The actual taking the steps and bonding yourself in, you're going to see, is not that complicated once you understand the principles. But what's missing is that these linemen don't understand that there is current flowing in that grounded system. And that grounded system then is just like a system neutral. You could not get a lineman to go up to a system neutral or a neutral bus in a generator plant, or a neutral bus in a substation, or a neutral bus on a transformer, and open that bus and put their hands on both sides of that open bus. Nobody would do that.
Yeah.
But grounding system is exactly the same way. It's got current flowing in it, and if you open that circuit, you're going to have system voltage at that open. Or if you have resistance in that circuit, you're going to have a voltage that's going to appear on that system. And that's what gets these guys caught, because they get into an unexpected voltage on a grounded system, they say, hey, it's grounded, it's okay, it's safe to touch. It
Yep.
is not safe to touch if you don't understand what the issues are. So
Yep.
bonding yourself in solves that problem.
Great information, Jim. So let me just touch on a couple things here, and then we have a lot more to discuss here with Jim, and looking forward to that. So obviously, just a formal kind of introduction. I'm sure most people listening probably know you, Jim, but Jim's the senior consultant for the Institute for Safety and Powerline Construction. As we said already, probably the industry expert in grounding and bonding. And so we appreciate, Jim, you being here with us today, taking a little time out of your busy schedule to join us. Normally in these podcasts, we do a tailboard topic. And simply today, I'm going to touch on kind of high level what we're supposed to be doing in the industry when it comes to grounding and bonding. And so, as Jim mentioned, grounding is done for the purpose of tripping, right? For activating the relays and tripping the circuit offline. That's the purpose of grounding, right? And then there's bonding, which is used to eliminate differences of potential in the work area. And so, defining those two things separately so that we can understand when we're having conversations why we're talking about grounding and why we're talking about bonding, and that they are indeed two different things. Now, not that you can't install your grounding, that it also acts as your bonding as well, but they can also be two different things. And then, to your point, Jim, OSHA has told us since 2014 or so, that we should be installing our temporary protective grounds in an equipotential fashion, right? To prevent anybody from being exposed to hazardous differences of potential in our work area. So the bracket versus the EPZ, and I know you've had these conversations, and I've had them with you, and I've heard your conversations with others. But and you just named 20 different incidents where it's just not happening, right? We still have folks out there that, whether they don't understand the pathways, or they don't understand when they are applying their grounds, that they're actually creating current carrying circuits. But we still have a lot of people out there making mistakes and not getting this stuff right.
Yeah, and I want to add a little bit more to that what you mentioned about OSHA.
Okay.
OSHA actually, when the rules for 1910-269 came out in 1997, you remember OSHA itself was established in 94 or 74. I'm sorry. Yeah. I forgot. You see, I'm getting old. Matter of fact, I was already a lineman before OSHA was formulated, and when OSHA first showed up at our service center, it was a big surprise. Who are these guys? Matter of fact, one of our old line foremen, when we had our next safety meeting, they told us about all the violations that we had been charged with by OSHA. He stood up in this room full of 60 linemen smoking a Pall Mall and said, "Well, who is this Mr. OSHA, and how long's he been a lineman anyway?" That's what we thought, about OSHA.
Yeah.
But when OSHA came out with 1910-269, which was in 1979, they said there was a rule in there that said when grounds are installed for the protection of personnel, they shall be arranged in such a way that no one is exposed to a difference in potential. And everybody looked at that and they said, yeah, well, of course, you hang your grounds and you've done that. But people kept getting killed, and they were getting killed on their grounds. And OSHA got just a little bit more sophisticated about it. And because of the relationship with OSHA and the guidance of a lot of experts, including Brian Erga, who had done, now retired, who had done a lot of the testing in the industry at Puget Sound Electric, helped OSHA to understand the language that needed to be used as far as I'm concerned. And then OSHA said, "Oh, well, here's what's missing. Let's just put a title on the rule." So in 2014, when they came out with some revisions to the standard, they entitled an existing rule, which I think is 1910-269N3.
Hmm.
I miss the numbers a lot.
Nope, you're
And
right.
it was entitled equipotential grounding. And we started to get questions, how are we going to meet this new rule requirement for grounding? And we said, well, what rule is that? And they said the one for equipotential grounding. We said, well, look, that's not a new rule. It's been around, since the evolution of the OSHA standard. It just never had a title on it, and everybody was misinterpreting what it said. But when the rule said shall be arranged in such a manner that no worker is exposed to a difference in potential, that was the demand that the law required of employers to ensure that their workers were being protected by equipotential grounding, because it was the only way that you could ensure protection. Now, I want to add one more thing to that. I know, and I know, Mark, you got a couple of questions that you want to get answered before we get through this podcast. But listen to this. We have known since Bonneville Power did some of the first legitimate scientific testing on grounding of circuits that bracket grounding did not ensure protection of the worker. And that's exactly what their conclusions said. And in the conclusions to their testing, they also said, but if you install a bonding connection from the pole to the neutral or the pole to the static, it does ensure protection of the worker. And they wrote that, and it was published by the IEEE in 1955.
Wow.
1955. And then in 1988, Puget Sound, which is where Brian Erger comes in, and once I met him and I studied with him, and he taught me a lot about what they had done in their testing, and I learned a lot from him. In 1988, they repeated all of that testing with a little more sophisticated style and equipment, and you know what they found out? That 1955 testing was exactly right. You could not ensure protection of a worker with bracket grounding. You had to equipotential ground in order to ensure that that worker was protected. And that's the issue here, because over the years, and I hear this all the time in the 20 years that I've been teaching equipotential grounding, people object to the idea that we don't need bracket grounding. So, well, first of all, go ahead and bracket ground. It doesn't hurt to bracket ground as long as the structure that you are on has an equipotential bond built in there somewhere to put the pole and the conductors at or very near the same potential. Because if that potential between the phases and the structure is high enough to break the resistance of your skin, now current can flow. And just like you said earlier, Mark, we know that grounding has current flowing in it in our systems, whether it's transmission, distribution, substation, generation. If it's a grounded bus, it's going to have current because we bond everything together to create an incidental bonding system, which means that our grounds are simply parallel to our system neutral. And electrically, it's going to divide current in whatever those pathways are available. So there is always going to be current there. So the problem was that if we bracket grounded, this current is still flowing in this system, but we have no way of knowing what that level of current is. And we have no way of knowing what the voltage is going to be that's going to be developed by that current flowing in that system. But if we bond, and if we put that arrangement right there on the structure with us, and we limit the length of those conductors, and if we bond that conductor in, we can control that voltage and keep that voltage lower than what I call the threshold of electrocution. If the voltage cannot penetrate my skin, current cannot flow, I cannot get hurt. If I'm just relying on bracket grounding that's thrown up on a structure or two away from me, that's the crapshoot. I have no way of knowing how much resistance is in that system and what those potential differences are going to be. On the other hand, testing has shown us over and over and over, if we build that bonding connection close to our workspace, that voltage is going to be so low that it won't matter what the current is. It won't matter if it's 4 milliamps or 40 amps or 400 amps. You cannot be hurt by current if the voltage cannot penetrate your skin and let the current flow.
And I think, obviously, Jim, you have, like you said previous, you have a way of kind of connecting the dots and making it make sense that people can understand. You hear a lot of different things out there from a lot of different people when it comes to grounding and bonding. And I think a lot of times what's missing is the why, right? Do this, put this here, do this. Why? Why do I need to do that? And once people understand the why, then I think they can start to associate with, okay, now it makes sense. Now I understand why they're telling me to do it this way. Even though when we talk about bracket versus EPZ, bracket grounding, I've heard everything, brackets are the walls, right? Nothing can go past, all these type of things, right? And there's companies, still today that live by bracket grounding and think that, everything is going to be okay. And those are the folks that we need to crack the shell on and get them to understand the why and why they need to change or do additional. Again, like you said, if you want to hang brackets, hang them, but understand that's not good enough.
Yeah, some of those people that are still doing it are our clients, and
Yeah.
they don't want us teaching grounding. We'll teach bare hand and hot stick and supervisory control and talent and soft skills and all that other kind of stuff. But we don't need you to tell us about grounding because they don't want to hear it, because they think that it's real because it's been around such a long time. But it's just like you said, and I did the same thing when I was a lineman, and they tell us to bracket ground on either side of us between the source. And I don't know what I was thinking. I never really thought about it. Does the electricity just stop at the grounds, or what happens? I had no idea one way or the other what was actually happening, because nobody ever explained it until you sit down and you start reading about it, and all that literature is out there for you to read, that a ground circuit that becomes energized is no different than any other circuit, with the exception that it's grounded. If when in our normal systems from our substations out or to our substations, the amount of current that's in the system is determined by our customers or the utilities customers. How many light bulbs are turned on? How many motors are turning? That's what determines the current flow. And then everybody out there knows the principles of current flow in that operating system. Well, with a grounded circuit, it's exactly the same thing, except that there's no limit to the amount of current that can be developed, because we put grounds on intentionally to drive that current up high enough that it trips those breakers just as fast as we can trip it. But the problem is that that current is flowing at the speed of light. So it doesn't stop at the grounds. It goes to whatever it's connected to, and it's the speed of light, and it's still going to go through the system. And all you have to do is look at a fuse curve or a curve in a substation breaker system and see, oh, the best we can get is 3 cycles to clear, or 5 cycles to clear, or even more. So how much time is that? That's three. Imagine how much, well, let's say the other side of the question is, so how much time does it take to electrocute you? The same amount of time that it takes to clear that breaker. So if that current is flowing at you at 70,000 amps of current for 3 cycles, that current's going to split, and it's going to create potentials in your work environment for that 3/60th of a second, and that's all it takes. So if you can't control that voltage, you cannot protect yourself from that system. But that's the reason why we call, and you mentioned it earlier, brackets, we call them tripping grounds. Well, we can still put those tripping grounds up as long as we have the pole bonded where we're at. And I think that the biggest question is, because we still have a lot of customers that say, okay, we'll do EPZ, but we don't want to get rid of brackets. And we say, that's fine. Put your brackets up. And then if you do that, you have to get your engineers to figure out the if, ands, or buts about current flow and resistance and how much current you're going to have and resistance of a circuit. But there's many times where you can get away, and I'm not saying get away in the sense of cheating the system, but you could put your brackets up one span away, and you can make a connection from your neutral to the pole, and you would be at equipotential at that pole. But the voltage between the grounded phases and the grounded pole is going to be a little bit higher because of the distance required to get that phase grounded all the way back to those brackets. And that's the thing that we're looking to do, is to limit that distance, limit those lengths of those conductors so that that voltage is low. Because what is not being taught is that the amount of current that is allowed to flow across that bonding jumper onto that structure is the current that the worker is going to be exposed to, just like the voltage. So the way that we test a ground in our grounding system is we take that ground, we put it on a ground tester, and we apply 200 amps to it, and we measure the voltage that occurs across that ground. So that's officially referred to as the voltage drop. We call it voltage rise because where there was no voltage, when we applied a current to that conductor, there is a voltage now. So if I take a voltmeter and put it on one clamp and the other end on the other clamp, and I've got 200 amps flowing through there, there's going to be a voltage, and it's going to be right there on the tester, and that voltage should be about 5 amps. Just saying, for the purpose of this discussion, it's going to be different depending on the length and the size of the conductor. Well, if it's supposed to be 5 amps, but it's 7 amps, well, there's a problem with that connection. But the longer the conductor is, the higher that voltage is going to be. I think I said amps, and I meant to say volts. So if I put that connection between the phase and the neutral and the pole, the voltage drop across that conductor is the voltage that I'm going to be exposed to in my work environment. And if I kept that voltage down to 7 volts, I'm good. I'll never feel that. Now, I want to say one other thing here too, because every lineman that I have ever asked this question, and we'll take, we sometimes we ask it about nighttime putting a splice together on a grounded 3-phase circuit, when you're restoring wire, or being in a ditch and putting together a concentric across the splice that I just made. And every one of them will tell you the same thing. And we say in the dark because you can see it. When I take the two ends of that neutral and I touch them together in that clamp or in that splice, what's going to happen? And every lineman will say the same thing. You get a little spark. And I say, yeah, what does that mean? And they'll start thinking about it and they'll say, oh, yeah. Well, that means there's current on that circuit. Where's it coming from? It's grounded. Yeah, it's grounded and the voltage has collapsed, but the current is still there, and I'm making and breaking a connection. Now, fortunately, because of the multi-grounded systems that we have, the voltage in that open concentric, or when I'm putting those splices together up on the 3-phase overhead, stays very low, but we don't know what it's going to be or how low it's going to be because we have no idea what that grounded system's performance is like. But for all these years we've been doing that and seeing those sparks, we never even thought about the fact of what that actually meant. Every time we make those connections, that voltage is there in that open, but it's just never been high enough to break the resistance of our skin. And so we've been cruising along thinking there isn't any risk, and there is risk. But we can guarantee that that risk will not affect us by making one more connection. And that's simply that bonded connection that we're at. Now the underground, that's uh, a whole different issue, because if I'm on the top of a pole, all I've got is sky around me. I don't have to worry about bonding sky to my pole. But if I'm sitting in a ditch, or if I'm on my knees in front of a pad mount transformer, I have a real big problem there trying to bond everything together. So it's hard to control that risk. So I might as well tell everybody right now that Mark and I have been talking about doing a series of these podcasts where we're going to address the peculiarities of each of these environments. And we're going to do a podcast series on grounding for personal protection in the underground, and how we create that safe environment to work in, or what our alternative are.
And that's coming up in a couple of episodes. And real quick, before we get any further, got to talk about our sponsor one more time. Gritty Tools is the sponsor today, eliminating workplace injuries one tool at a time. The GT 330, 660, and 770 lifters make moving and changing out control equipment a breeze. Lifters are battery operated, and there's no more need for annoying power cords in your work area. So stop wearing out your employees and let the tools do the work. For more information, give Gritty Tools a call at 866-4GRITTY, 4GRITTY, or if you don't see the numbers or the letters on your number pad, it's 447 or 866-447-4889, grittytools.com.
I'm amazed at some of the tools that these companies, these entrepreneurs are bringing out, into the industry. Because I'm one of those linemen that built half the world using 7 hand tools, and
Yeah.
and now we've got truckloads of tools that we can use, and every one of them takes a lot of that. All linemen that are my age are hobbling around now on bad knees and bad backs, and everything else, because we wore ourselves out working with hand tools.
Yep.
And then as technology evolved, now we can reduce a lot of that risk that creates those long-term injuries on our workers, and you can enjoy your
Yeah.
retirement a whole lot.
But a lot of that, you talking about, like especially like the battery lifters and stuff like that Gritty has. You sacrifice these larger electrical mechanical things that were big. You knew they were obviously heavy for this smaller footprint, but it's still heavy. It sometimes in some cases even heavier, and you don't realize what you're dealing with in a lot of cases.
Well, then, if you're a rigger, all you do is put up a little set of blocks, and you pick up the heavy things with a little set of blocks.
Yeah. Yeah, for sure. Let's build on this, Jim. I got some questions here that we've gathered together, and let's go ahead and talk about some of these and get your input. So, how about a little bit about your history with grounding in your career? Maybe go through that a little bit. I think you've touched on it a little bit already, but
Yeah, and I want to honestly say that, to say that I was always a big advocate for equipotential grounding, I'm saying that's not necessarily true, because first of all, I was never taught that we should be doing it. In fact, that grounding wasn't really a big deal until utilities started to make it a big deal, because they read the new OSHA standards, and so they said, okay, let's make this official. Here's your grounds and stuff like that. So this really does kind of tell you what we thought about grounding, and in particular what I thought about grounding. I was a foreman on a transmission crew, and we had a car hit pole on a main throughway in Fort Lauderdale, and we had transmission on the top, and then the Muni had an underbuilt distribution. So we met the Muni crew out there, and we were all going to work that structure at the same time, because the structure was broken. We had to put a new pole up. We owned the pole, and they were going to have to move their stuff too. So when we were standing there doing our tailboard, which we had always done historically in the industry, but we didn't ever talk much about grounding. But he asked me the question. He says, "Hey, are you guys going to ground your transmission?" And I said, depends on where Hooters is at. And he said, Hooters? What does that have to do with it? And I said, well, our safety guy rarely gets out of the office. And if we're past Hooters, we're never going to see him. But if we're between Hooters and the office, he's probably going to stop by. So that's when we ground.
Nice.
We're not going to get in that trouble. See, so we just had a sort of, what do they call that, laissez-faire attitude, about
Yep.
grounding, and just thought it was something that was really perfunctory. We didn't really understand, how important it was. But just like a whole lot of other people, everything that we were talking about just in the last 15 minutes about those little sparks and the fact that current's always flowing in that grounded system. I, just like everybody else, had never had anybody that got hurt or especially killed by their grounding, and part of it was because we weren't grounding,
Hmm.
anything, So and sometimes we work it like it was hot, or because we were isolating. Now that actually is a legitimate practice that when we start talking about grounding, we have clients sometimes that get so stuck in the idea of grounding they forget that there are some other or alternative work methods that they could also use, and isolation is one of them.
Hmm.
So, I ask our clients when we're talking about substation grounding. I ask this question just to get people thinking about it. So let's say that I've got a big substation transformer sitting in the middle of this substation, and I've got these big goabs and vacuum breakers on either side of it, and I've opened the goabs or these gang operated switches on both sides, and there's a 2.5 or 3 foot gap between those switch blades. And then I go and I disconnect the couplers and I pull the fuses out of the controller and I put a lock on the operator. There's no possible way that that switch can close. And then I go over and I spend an hour and 10 minutes grounding all of the bushings. And I say, why? Well, we have to. Why? The switches are open. It's isolated. Nothing can happen. There's no such thing as induction on a transformer, so that's not going to happen. I said you may get skin induction if you're in a 345 kV substation, but grounding a bushing is not going to stop that. And besides that, it's not going to hurt you. That's just what we call capacitive coupling. It's
Hmm.
just voltage. It's aggravating and it's irritating. And there's some companies who say zero tolerance, but capacitive coupling will not kill you. There is
Right.
no current flowing with it. It's just aggravating.
Hmm.
So why do you ground it? What gets people thinking? Isolation is a legitimate form of protection. But if we're just throwing up grounds and we're not equipotential protecting those workers, then we actually have less protection with that bracket grounded system with no equipotential than we would if we just created isolation. We'd be even safer. But everybody forgets that that isolation might be one of those opportunities. Now, when I was a lineman, we used to isolate all the time, and isolating by opening up a switch and taking the barrel out of it in distribution, or opening up a set of switches, in a substation, and we would just work that system isolated. And so there wasn't any opportunity to find out that grounding wasn't going to work. And then we also, and OSHA recognizes this too, our switching and tagging procedures are set in stone and they are extremely accurate. Now, once in a while, somebody screws up and closes a switch, and that's a horrible thing to happen. And companies will stand down their switching and tagging until they find out what happened and whose head's going to roll and who screwed up, over something like that. But those kind of things in isolation are one of those things that provides that level of protection for us, and that's what I grew up on, and that's what I lived on. But when I found out, and as I related earlier, when I found out that bracket grounding, and I'd spent all those hours doing it, was not ensuring my protection, and further that we knew that equipotential grounding did ensure protection, that's when I really got involved in it.
How about the biggest misconception about grounding a de-energized line?
Well, I think the biggest misconception is that grounding that line, we know that it collapses the voltage, but that stops the current from flowing.
Hmm.
That de-energized line that's grounded is safe, because it's not. And we've already talked about that earlier, and that's the one that surprises me the most. I take when we do a lot of training for companies, and in our presentation, one of the things that we do is we have a graphic of a strap hoist on a system neutral, and we cut it and we open it up, and we walk through that and we say, okay, now what's going to happen? What do you need to do? And they say, yeah, we got to map that out. And they say, why do we got to do that? Because if we cut it and open it, there could be system voltage between those two open ends. Absolutely right. And then I say, so what's the difference here on a grounded system collected to the neutral? And I watch people's faces all the time go, man, you got guys out there with 10 years of experience and working at top of a pole and never thought about that because
Hmm.
it's just not one of the things that's been discussed. And
Yeah.
so that's probably the thing I think that's most important that they understand.
Hmm.
We also have I tend to teach from the perspective of principles of current flow in a grounded system, and what we try to get everybody to do is to apply those principles and understand what those three very simple principles are, because if you understand them, you can apply them to every grounded environment and you can solve what the hazards are going to be and what you need to do.
Hmm.
And that first one is that that current flows in every available path. When you when you have a certain number of available paths in accordance to the resistance of that pathway.
Yeah.
So if I've got a static and a neutral and a pole bond and a street light pull off and a residential circuit and a transformer, every one of those are pathways, and each one of them has current flowing through them, and they're all going to have current contributing to the total amount of current that flows in that system. And if I ground that circuit, I haven't. I've collapsed the voltage on each one of those, but that current is coming from every other pathway connected to that bus, that I'm working on. So we know that it takes 50 volts to break the resistance of my skin, and we know that current, and that's principle number one, that it takes 50 milliamps of current to rise to the level of risk to the worker. So these are universal numbers that we use because we have to start from somewhere to try to be able to estimate the level of risk.
Hmm.
So 50 amps of voltage breaks the resistance of your skin. 50 amps of current can cause a medical emergency because it can stop your heart. That current flows in every available path, and that the only way to protect that worker from that voltage is to bond those paths together so that the voltage is the same between each one of those. So if we understand that the nature of current flow in a grounded system, then we can understand the nature of the risk and what we have to protect ourselves from.
Jim, I find it funny. We were talking about the training and the current on a grounded system already. So when we were at the tower, you said, "Hey, do you think there's any current on this ground on the tower?" And all of these guys were like, "Oh no, it's the ground." And you put the meter on it. It was an eye opener for those guys, and it was an eye opener for me too. And it goes back to what you're saying here. Just because.
Yeah. We had a client that we won't tell you their name. We were writing their grounding program for them after we did an audit of their grounding, and we found out there were a number of things that they weren't doing that they should have been doing, and one of those was, especially in their transmission work, and one of those was testing for voltage, because that's one of the requirements of the OSHA standard, is that you test for voltage before you ground. And so for the very first time, they went up a structure with a voltmeter, and they sort of just laid that voltmeter up there on the phase, and they got about 1200 volts. And I saw the two linemen look at each other, and I said, yep, it's there. And they couldn't believe that there was 1200 volts. And these guys had 20 years between them because they had never tested for voltage on that circuit. Hey, why is that important? Well, because if I've got 20 volts on a de-energized circuit, or that's being caused by induction, that's the same thing that I've got on an overhead static. So if I've got 4 of these in my histories on fatalities, a lineman climbing to the top of a structure and with his feet on the structure grabbing that static and being killed by it because he didn't realize that there was 1200 volts on that grounded static that was grounded somewhere else, and when he opened it up, he got killed by it. And then the other one is some utilities that this was a substation utility we were working with and helping them develop their grounding practices, and I showed them several photographs in my training presentation of amp meters on grounds on transformers and columns with 18, 19, 20 amps, 36 amps, 40 amps of current flowing on them. And we had probably 150 years of experience of substation technicians in that room, and nobody had ever seen that. And our second day was inside that substation and looking at the different requirements for grounding and bonding and what we had to do to protect those workers. And everybody showed up about 20 minutes early, and all 20 of them ran out there to the substation with handheld clamp-on amp meters, clamping on transformer grounds and column grounds to see how much current was there. Never had done that before because that fact had just escaped them over the 100 and something years that utility had been, in business. And that's the nature of our base of knowledge that has created some of the work environment risks that we have. Until everybody gets the message and understands it. I thank you for reminding me that, Jerry. It's funny because nobody got hurt, but in one sense, it's not funny, but it's always
well. Yeah, it's eye opening for people when you start teaching someone the why, and all of a sudden just the just because we do this just because we do this because I said so kind of thing. And when they start learning the why, they start understanding why this is important to do or why we're supposed to do it. It's eye opening, and then it changes the way they think about what they do for a living.
Building on that, companies that require bracket grounding, maybe in the opinion of, we've always done it that way, right? We require bracket grounds because that's always just what we've done. But what do you say there, Jim, as far as, kind of like Jerry was saying, hey, that just because, right? We require bracket grounding just because.
We have a lot of clients that we go to, and we'll find them doing some things that are extra and way above and beyond what they need to do in order to accomplish worker safety.
Mm-hmm.
And a good example is you find companies that got 23 kV and they're using class 3 gloves. And we say, you don't need class 3 gloves. Class 2 gloves work just fine. And then suddenly they say, oh, yeah, but they don't want to change because they feel like they're backing up. So we've got this history, since the late 70s of using bracket grounding, and probably before that for a lot of these utilities. And when you tell them they don't have to bracket ground anymore, that makes people nervous because they're used to standing there at that structure and looking down there and seeing those grounds with flags hanging on it, and looking down there and seeing those grounds with flags hanging on it, and with a feeling of safety, and they don't want to eliminate that. So we said, look, you can still ground, but here is and this might be another one of the things that we hear that are common and mistaken. What we tried to get everybody to understand is, and put this in their liturgy about grounding, is that grounding trips the circuit, bonding protects the worker. Well, and here's another one that people miss. If your engineers tell you that you have to have a parallel set of 4/0 in order to manage fault current estimate for that circuit, I can put one set of 4/0 grounds on structure one, and I can put another set of 4/0 grounds on structure three, and what do I have? I have a parallel set
Parallel.
of 4/0. So yeah, that's still that's another way that I can use my brackets.
Yeah.
But the brackets are there for grounding, the purpose of grounding. Now, we don't have time to get into a discussion about where the grounds have to be placed from the source and all that other kind of stuff because that discussion gets really ridiculous when you think about how fast current moves on a circuit at the speed
Yep.
of light.
Yep.
So, whether I put them on my right hand side 15 feet away or my left hand side 15 feet away at the speed of light, there's not going to be any difference between
Mm-hmm.
where I put those bracket grounds. But bracket grounds don't hurt anything as long as you understand that grounds strip the circuit, equipotential or bonding protects the worker. So
Yep.
somewhere in that bracket system, there has to be at least one connection between the phases and the pole. One
Yeah.
more connection between the phases and the pole. So if one set of grounds will operate the circuit, just like you said earlier, I can use that one set of grounds right where I'm working and add one connection from the neutral to the pole. Or sometimes some companies want to go from the phases to the pole and then to the neutral. Doesn't matter which way you do that, as long as that one connection is there, and now you're good. So
Yeah.
go ahead and use the brackets if you want to. Doesn't hurt a thing. It's taking extra time, and if you think of it from that perspective, which I don't want to get into a discussion either. Oh, it takes too long to do this, because that's not why we do safety. We do safety to protect the worker. But there's some
Yeah.
effort that it takes to put those sets of grounds up, and they may not be uh, uh, creating any additional safety for the worker. So it's something to discuss.
Yeah. So we got a couple minutes left here. Maybe just two things to touch on here. So we haven't we've talked a little bit about it today, but so what about induction, right? So when you're talking grounding versus bonding, do I ground? Do I need to bond? What goes? What about when you're talking about induction?
Yeah, and induction is really not very well understood. And when we do the transmission section, when we do training, or when we're writing programs for our clients, we do a pretty detailed description of the whole concept of induction. And there's really two types of induction that both they can exist independent of each other. One of them is called capacitive coupling, the other is called inductive coupling. And capacitive coupling happens when we have a crossover on a line or short parallel where or driving a truck into a substation and that truck gets a little electrical charge on it, or the top of a transformer gets a charge on it, or structural steel gets a charge on it. And when we touch it, it equalizes our body charge, and we might get a little bit of a shock, off of that. That's that capacitive induction or capacitive coupling. Voltage only, no current element. Magnetic induction is the one that will kill you. Magnetic induction means that the induction itself is at a high enough and usually has the voltage to support it with enough current to create a magnetic field around the conductor that can transfer to a nearby or couple to a nearby conductor, which might be your grounded circuit.
Hmm.
Well, that ground is only going to collapse the voltage, so you won't have that capacitance there, but you still do have the current flow that's going to be there. So managing induction is a little bit different because where and I tell you what, one of my bigger issues is that a lot of people call that capacitive induction static. It's not static, and the
Hmm.
reason why that's an important differentiation is that static won't kill you. but induction will. And if you're
Hmm.
getting shocked, there is induction in that work environment, and you have to know the difference between capacitive and magnetic coupling. And the easiest way to tell is an ammeter, because if
Hmm.
I ground a circuit and I put an ammeter on that ground that I use to ground that circuit and there's no current flow, then that was capacitive coupling, and I collapse that voltage. Where if I put an ammeter on that ground and current is flowing, now I know I have a magnetic element, I have a current element, and I have to treat that conductor just like it's a current carrying neutral.
Hmm.
If I open that circuit, then there's going to be a problem. And I think one of the funnier things that I hear all the time is I hear people say, "Oh, we put a set of grounds on that structure, and 8 feet away we touched the conductor and we got shocked." And they're saying those grounds don't even collapse that voltage, but they don't understand what's happening. That magnetic field exists all around that conductor, and it may reach out there 8 or 10 feet. And if you're in an isolated bucket and you're booming up, your body becomes electrically charged, but
Hmm.
it's not going anywhere. You don't feel it until you touch that grounded conductor, and now you're discharging that voltage on your body. The
Hmm.
first thing everybody thinks of is, oh, I got shocked off that conductor. No, you shocked the conductor with that induction field that's on your body. So when it comes to working, especially where you work around transmission, or if you're stringing conductors or working in substations or working near transmission, your crews ought to have a very good understanding of the nature of induction and how to control it, because that's one of the things that OSHA added in 2014, is that the employer must determine the level of induction, and if that level of induction is going to be a risk, then they must treat that conductor in accordance with section N, which is grounding. And if you're going to ground to protect against induction, then that grounding has to be in an equipotential manner to protect workers from that induction current if that ammeter says you've got current flowing.
So last question, Jim. We got just a couple minutes left here, but and so hopefully, maybe you can sum this up at a high level, and we'll dig into it further when we start through our series. But maybe some. So, what are some challenges both in designing and maintaining that grounding system, right? Because a lot of times when you're working out there, through the evolution of your workflow or your work process, the way you initially designed and installed your grounding system might not work for the evolution of that job, right? It's
Yeah.
not one of those things you can just throw on there and say, "Hey, I'm good from A to Z," right? I got to understand what's happening through that whole project or job or task.
And we call that looking for the gaps. So so let me explain what a gap is. If I open a switch and I create an air brake, that's a gap. And if I get across that switch, that gap is going to have voltage across it, and the voltage depends on what the system voltage is and all the other stuff that goes along with that. So we talk about looking for the gaps, and that means, just like you said, if when I'm doing my tailboard and I'm working my way through my project and through my task, uh, you're going to be looking for the gaps, because those are the ones that you have to bond out, and you have to determine whether or not you're going to be creating any gaps in your bonded system, in your grounded system, while you're doing your work. I've got two cases that we cleared just this past year that in both of those cases, they grounded and they bonded themselves in, but they didn't realize that once they were going to move a jumper, when they lifted that jumper, they opened up a gap, and the men got between the jumper and they were electrocuted.
Hmm.
And they said, "How could that happen? We were bonded in." Well, not until until you open that jumper.
Right.
So you got to be able to stand back, look at those pathways, and say, here's a gap, or here's a potential gap, or here's a gap that we're going to be making. So we need to remember to bond here, bond there, or move our bonds out a little bit farther, so that that jumper that we're going to move is going to be inside of that inside of that bonded in area, or sometimes we call that the borders of our grounded and bonded workspace.
Yep. Well, Jim, it's been an hour already, so
Just
as I
like
said,
that, man.
yeah, just like that. And so, hence, I think why we're going to continue this conversation. This was kind of just to wet your whistle and get people, hopefully thinking about these things. And we talked about a lot of good stuff. I'm going to be listening to this one again, maybe several times, because I try to, like I said, every time I listen to you or talk to you, I learn something new, and or you say something or we talk about something a little bit different. I get another little piece that, oh, now I know why he said that the last time we talked. So it's just an ongoing evolution of continuously evolving this process of grounding and bonding and understanding how they work together, and how ultimately they protect us, hopefully, from the possibility of having a really bad day out there, right, if we don't do things the right way. So
Yeah, I'm going to add something here too. I'm hopeful that maybe we'll have 1,000 people see this, and maybe we'll have 100, and maybe we'll have 10. I don't know.
right.
And there's no doubt that everybody recognizes that ISPC is in the business of selling consulting and products. But I don't want that to stop you from asking a question.
Mm-hmm.
If you saw this presentation today and you saw something or heard something that concerns you, but you're not the person who makes commitments to spend money to buy consulting, we don't want that to stop you from getting in touch with us and asking an opinion.
Sure.
So I want to encourage you, and I know that Mark and Jerry are the same way. And Jerry,
Yep.
Jerry is like what, your manager of sales or something like that? Don't you have that? Okay.
Yes, sir. Director of sales.
Yeah. So
Yeah.
he's out there selling product, but he has the exact same feeling that I do. We don't want you to endanger yourself or your crew because you're not the person who writes the checks.
Yeah.
So it doesn't take us, much time at all to answer a question for you and point you in the right direction. So don't hesitate to do that.
And if you want to get in touch with Jim, it's Jim at ispconline.com. Jim at ispconline.com. Guys, real quick, one last time, we got to thank our sponsor for letting us do this. This week's sponsor, or this episode's sponsor, is Gritty Tools, eliminating workplace injuries one tool at a time. Now, Gritty Tools has the GT5000, is the fully air-operated wire puller that is mounted to a trailer, and at 4,000 pounds, it can easily be towed with a half-ton pickup truck. And with 1,000 foot of steel cable and an onboard 185 cubic feet per meter. Is that it, CFM?
CFM.
Ingersoll Rand air compressor. There is no longer a need for a pull line. Its small footprint makes even the tightest workspace accessible. Don't take it from me. Take it from the experts. Ask them all about it. GrittyTools.com, GRITTY tools.com, or give them a call, 866-4GRITTY, 866-447-4889. Now, as always, we have to tell you that the views and opinions shared in this podcast are the personal viewpoints of the participants and may not necessarily reflect the stance of the Institute for Safety and Powerline Construction or its staff. It is highly advised to consult your company before implementing any actions or policy changes. And please support our sponsors bringing this content to you. For more episodes of ISPC Tailboard Talks, subscribe to your favorite podcatcher, and be sure to leave a review. We'd love to hear from you.
Wow. You gotta go back to English class. But anyhow,
and that's my first language. I don't know what's going on today.
Well, as Jim said, if you got a question, don't hesitate to reach out to us. We're always happy to answer questions. We want to make sure you're doing the right thing out there, and we want to make sure you're keeping your folks safe. So, until next time.
Well, before you say goodbye, if you have any questions that you want to ask experts, Jim Vaughn Mac Turner, Mark Forster. I'm not an expert on anything, but a couple of things. Give us a text, give us an email, give us a call. We'd love to hear from you as far as your questions, comments, or rants, if you have any on that. And if you want to be, if you want that to go out over the airwaves, we'll put you on the podcast as well. We'll read your question and answer that. I know Jim Vaughn does a stump the chump thing a lot of times, and we'll see if we can't stump him during the 6-part series. 6-part is it or 3-part?
All right.
The mini 5-part.
5-part, 6-part.
Whatever.
Stay tuned. It's coming. Until next time, I'm Mark, your host. Catch you later, Jerry. And
See you
we'll catch
guys
you next time on ISBC Tailboard Talks.